All right, so yesterday we had our first lecture on partial differential equations. Today we shall be going on further and trying to understand what all, first we will try to understand the classification of second order PDEs, and then we will see how far we can reach. Very good, so let me start off by sharing screen. And okay. Hopefully my sound is better today. And yeah, so we will move on to try to understand this here. So, yeah, I'm sorry, give me a second. Let me just try and sort this out. I'll make sure that I get this right. So let's do a new one today. All right, so what we were going to do today is we are going to start off with a general second order equation. So let's say second order PDEs. We will consider the most general second order partial differential equation that is linear but not necessarily homogeneous. So let's write this down. So most general. Most general PDE of second order that is linear but not necessarily homogeneous. So this is going to be some Aij of the variables up, del 2y, del u1, del uj, ui plus uj, plus some function ui, y, and del y, del y is equal to 0. Here, there is a sum implied, of course. Let me just write this down. Ij equals to 1 to n. Now, what does linearity mean? Linearity means that if you perform a scaling of y going to lambda y in a PDE, then each term is going to scale as alpha. Then the PDE is called a linear, homogeneous PDE. Okay. If in addition to this, this particular scaling, there are terms that do not change, the equation is called linear but non-homogeneous. So let me also write this down. Linearity. Y goes to lambda y, say alpha y in a PDE. In each term scales as lambda, as alpha, then PDE is linear homogeneous. Linear homogeneous. If there are terms that don't scale, don't change, then PDE is linear plus, but not homogeneous. But not homogeneous. Okay, so that's what we mean. Now, what we're going to do is that we are going to assume that this function y of y, which is a function of the UIs, when we are speaking of a physical system, then this would have the required properties like, the second order partial derivatives would be symmetric in I and J and so on and so forth, okay? So those would be required in a physical system. In that case, if the only second order thing, so del 2y del ui del uj is equal to del 2y del uj del ui, then you can see that we can safely say that aij is symmetric, right? So as you know, if you have a symmetric term multiplying an antisymmetric term, that gives us a 0. So what this is going to be is that these coefficients aij will be symmetric. Thus, for each point you want to uj, aij is a real symmetric n cross n matrix, and hence the eigenvalues of this particular matrix are going to be real. Okay. So the partial differential equation, what is going to happen is it's going to be classified by the signs of these eigenvalues, and the nomenclature that we are going to be dealing with is going to be very similar to that you have previously seen in, conic sections and things like that. Okay, so so let's write down the logic once more. So this is symmetric. So for each point, you want to sorry, just give me a second. Just take this thing off. And okay. So you want to UN aij is a real symmetric n cross n matrix, and hence the eigenvalues are real. PD is classified by the signs of these guys, signs of eigenvalues And the nomenclature is going to nomenclature would resemble conic sections. Okay. So now let's remember what a conic section, conic section is defined by conic section. So that, if you remember, this is going to be Aij, Xi, Xj plus Bi, Xi plus C is equal to 0. Okay. So this is going to involve a real symmetric 2 cross 2 matrix with eigenvalues lambda 1 and lambda 2. And this is going to either represent an ellipse or a hyperbola or a parabola, depending on the sign of these lambdas. Okay. So real symmetric 2 cross 2 matrix Aij with eigenvalues lambda 1, lambda 2. And, so this is going to represent either, say, an ellipse if what you have lambda 1 x1 prime squared plus lambda 2 x2 prime squared is equal to 1, and all the lambda i's are greater than 0. Or you can have a hyperbola if lambda 1 x1 squared, let's say primed, plus lambda 2 x2 prime squared is equal to 1. If lambda i's are not equal to 0 and lambda 1 comma lambda 2 are less than 0. Or finally, a parabola if lambda 1 x1 squared plus b lambda 2, so bx2 prime is equal to 0. These are the sorts of equations that we are going to get, okay? So these are the sorts that we have. So x1 prime and x2 prime that I've written out here are obtained by an appropriate rotation followed by a translation of the origin if required. So, what we can see is that, we can, if you go back to this equation that I wrote down at first for you, this particular equation. So, we can see that any point Aij can be diagonalized by an orthogonal transformation. So if the coefficients are dependent on ui, so the eigenvalues can differ from a point to point in an n-dimensional space. Okay, so so since these guys can change at each point, we would need to classify a given partial differential equation at some given point. Okay. So this is something that you need to keep in mind. So now we come to trying to understand this. So okay, let's write this down. So at ui, Aij of ui okay? Depends on point, depends on specific points. So need to classify PDEs at a given point. So suppose at a point UI, say suppose U1, U2, U1 is equal to U1 naught, U2 equal to U2 naught, and so on and so forth. This particular PDE that we started off with, the PDE, is number one, a elliptic if all eigenvalues of A are non-vanishing and of the same sign. B, hyperbolic if all eigenvalues are non-vanishing and have different signs. There's something called ultra hyperbolic. This happens only for n greater than or equal to 3. This is the case if it is hyperbolic and only one eigenvalue differs in sign from the rest. And ultimately, parabolic if at least one eigenvalue vanishes, right? So then let's go back to the equations that we had earlier. Remember the equations that we were dealing with. So we had A as del 2 del x squared minus plus del 2 del y squared. Psi is equal to 0. B was del 2 del x squared minus del 2 del y squared. Psi equal to 0. And finally, C was del 2 del x squared minus del y of y minus of psi minus b equal to 0. It's very clear that the first one is elliptic. So these are already in a form such that Aij is diagonal. So we can just identify this. This is hyperbolic. And this guy has one equation, one of them equal to 0. So this is parabolic. Very good. So that was a classification. And yeah, so we will stop briefly before we go on. Yeah, one thing that I have to just quickly say is something that I did. I mean, made a small mistake in which I guess you guys have already seen. So the hyperbolic, conic section is not lambda 1 comma lambda 2 equal to 0, as you can clearly guess. It's lambda 1 times lambda 2 is less than 0. So either lambda 1 has to be less than 0 or lambda 2 has to be less than 0, okay? I mean, of course, that was obvious, but I somehow made a mistake there. All right, very good. So we shall be carrying on. And now next, what we are going to be doing is we are going to be starting out trying to say what the different sorts of boundary conditions are. Okay, now we shall be interested in trying to understand types of boundary conditions. Okay, so let me just write down types of boundary conditions here. So types of boundary conditions. Okay. So we emphasized earlier that differential equations that define these physical systems, if we solve them, they do not yield a unique solution that corresponds to a particular physical situation. In order to do that, these differential equations need to be augmented by, some boundary conditions. So if these boundary conditions are appropriate for the partial differential equation at hand, then this is going to yield a solution that is unique to the problem at hand. Okay. And we have also seen that it's important to stress that these boundary conditions have to be appropriate for the partial differential equation. It might, as we have seen, some particular boundary condition might lead us to, saying that there is no solution for the PDE with that set of, that particular set of boundary conditions, right? Okay, we also generally observe that when you are looking at small changes in the physical systems at hand, these lead to small, changes in the observables. So what we want is that the solutions of these partial differential equations should be stable when we do small perturbations of the boundary conditions itself. So we would be interested in formulating what kind of boundary conditions are suitable for the for types of PDEs, so that they will yield a unique, stable solution to the problem at hand. Okay. So first, what we want to do is we want to summarize the types of boundary conditions in principle that can be employed on the second order PDE. And we will see that there are these two kinds of boundary conditions on which, two kinds of boundaries on which a boundary condition can be specified. So these can either be an open or a closed hypersurface in an n-dimensional space. Then the boundary conditions will be further classified by according to the information that you provide on that, on that particular boundary. Okay, so if we specify the value of y, the thing that we were trying to say, the independent, the dependent variable, on a hypersurface, the information that enables us to evaluate this particular information will enable us to evaluate all linearly independent derivatives of y, which are tangential to that particular hypersurface. Turning this around, conversely, if you happen to know all the linearly independent tangential derivatives of y on a hypersurface, we can use that to evaluate y on it up to some, constant maybe. So the latter does not, constitute what you would call independent data. What can be specified independently is the derivative of y, which is normal to the hypersurface. So what we can do is we can classify, sorts of boundary conditions, and let's do that here. So let's start off with what we call Dirichlet boundary conditions. Okay, so this is what this is a value of the function f, not f, I call this u, as we y, as we were saying, is specified on a hypersurface. So that is one sort. Now, there is something called the Neumann boundary conditions. What are these? Instead of y, what we will specify here is the normal derivatives. The normal derivatives of y, that is del y del n on a hypersurface specified. Now, there are other things. We can mix things up. So, mixed boundary conditions. So for this, normal derivative of y on a part of the hypersurface and y on the remaining. So we mix these two up. Finally, what we get to is going to be called Cauchy boundary conditions. What's this? This is the function. Oops. The function y and its normal derivative del y del n are both specified on a hypersurface. Okay, we will get to this. We will try to understand this in a bit more detail. So let's look at an example now, okay? So let's do this. Let's look at an example. Let's take 3 independent variables, okay? So consider 3 independent variables, x, y, and z, okay? So x squared plus y squared plus z squared equal to 1. This defines a closed hypersurface. A closed hypersurface. Yes. So this is the unit sphere, of course. X squared plus y squared plus z squared equal to 1, and z greater than 0 is going to define an open hypersurface S1. This is also a hemisphere, and z less than equal to 0 is going to define an open hypersurface, sorry. S2. This is the hemisphere. This is hemisphere. This one, however, is the hemisphere plus its boundary. Okay. Very good. So now, let's try to figure out what the earlier things were. So if you were to provide y s is equal to 0, this is going to constitute Dirichlet boundary condition on the closed hypersphere, on the closed hypersurface. Closed hypersurface. Okay. So given this particular boundary condition, we see that all tangential derivatives, here just there are these two ones, that is del y del theta and del y del phi, of this must actually vanish, okay? Let me actually do something which is a little, makes life a little simpler for us, because I keep defining y here and y there as well. So what I'm going to do is that I'm going to call these guys so let me just redo this once. So let's call this x1 squared, x2 squared, and x3 squared. This is x1 squared, x2 squared plus x3 squared. This is x3, and this is also x3, and x1, x2, x3. Because we don't want to be repeating y's, right? My y is my independent, y is my dependent variable. Okay, so given this boundary condition, so all tangential derivatives so here there are two linearly independent ones. There's del y del theta and del y del phi. of y vanish. Okay. Conversely, given that del y del theta is equal to del y del phi is equal to 0, this would mean that y is equal to constant on this. Okay. Very good. So that is that. That was one. Number two is if we specify del y del r at on this S1 is equal to a of theta phi, this is going to constitute a Neumann boundary condition. So this is Neumann boundary condition on an open hypersurface. Okay. Similarly, if you have del y del r S1 is equal to b of theta phi together with y at S1 is equal to f of theta phi, then this corresponds to what? This corresponds to a Cauchy boundary condition. This is a Cauchy boundary condition on an open hypersurface. Finally, what you can do is, so you can put del y del r at S1 is equal to c of theta phi, and y at S2 is equal to g of theta phi. So this is specifying mixed boundary conditions. So these are mixed boundary conditions. Okay. So these are, if you wish, methods. These are the sorts of boundary conditions that we can put down. And so we will try and understand this more, and we will see how to evaluate things as we go ahead. So yeah, so that is what we wanted to do for now. And so we will have much more to do as we go ahead. So we will be we will look at trying to understand this in a more general setting. I will try and see if I can give you examples as we go ahead more. But hopefully the sorts of boundary conditions that are here and the classification at first and then the sorts of boundary conditions that are here are hopefully clear from what we did in the lecture today. All right, so I stop here today and we are going to resume very soon again. Thank you.